factoring that we are concerned about first, which is how to factor a quadratic expression whose leading coefficient, that should say, is 1. And then also be able to use factoring to solve an equation that involves a quadratic polynomial. So that's the first thing that we'll do. So our first climb up the mountain of factoring involves us first just sort of wrestling with the idea of what factoring even is in the first place. And so the first factoring technique that we ever learned was how to factor something using greatest common factor. Factor using, and I'm just going to abbreviate it GCF, greatest common factor of an expression. So, a typical problem in this area might look like this. And it'll say something like factor completely. I use the word completely in these prompts just to emphasize that if there is still factoring that's possible to do, then you're not done yet. Okay? But that may not always be the case when you see one of these problems online or whether you see it on the page in the exam. But implicitly, if it just says factor, you can always put the word completely in there in your mind. So here's what I'd like for us to think about factoring completely for starters. 24x to the third minus, let's see, why don't we do 21x to the fifth. So here's something that I'd like to factor completely, and it's only got 2 terms in it. We're going to talk in a little bit about a new method for factoring things that only have 2 terms in them, but this is one that we won't need that method for. So what should I think about here first? How should I think about the process of factoring this particular expression? What do I need to determine? First question is, do 21 and 24 share a common factor? What do you think? How do we answer that question? There are a number of different ways we could do it, but what would be one way that you could approach investigating whether 24 and 21 share a factor? Okay, so we might first say, what about oddness and evenness? Well, 24 is even, 21 is odd. So what do they not share as a factor? They don't share 2 as a factor, right? Because one is even and the other is odd, so it's not. The only way for 2 things to share a common factor of 2 is for them both to be even. So 2 is not a common factor. So the next factor that we might think about is the next largest prime number besides 2. What about 3? Well, does 3 go into 24? 8 times. Does 3 go into 21? 7 times. So yes, in fact, 3 is a factor that the 2 of these numbers share in common. So I'm going to just sort of put it in a box here. So we know that the greatest common factor of these 2 numbers is at least going to be 3, but that they might share something else. And to figure out whether they share something else, let's look at the other factors that we broke apart these numbers into. Do 8 and 7 share a factor? They don't share a factor. One is odd and the other is even, so they don't share a 2. But 7 has no other factors besides itself and 1. 8, if we were to break it apart, I'm just going to kind of write it this way, is only made up of 2's. And since all my 2's here are prime and my 7 is prime, that means since they don't share anything in common, that we must be done. So the greatest common factor of 24 and 21 is what? 3. Awesome. So that's the first observation, is that these 2 coefficients, 24 and 21, have a 3 in common that we should be able to bring out. So I'm going to go over here, and we're going to use this little device a lot today, the little factoring box. And inside of my factoring box, I'm going to write my 2 terms that we're trying to factor, 24x to the third, and then minus 21x to the fifth. And we've just decided that 3 is something that is a factor for both 24 and negative 21. And what are the cofactors? How much do I have to multiply 3 by to get 24? 8. That's this 8 from over here. And so I would have an 8 up here on top. And then negative 21 is going to give me negative 7. Okay, so now we've done the factoring piece for the numerical coefficients in this expression. What do we do with the powers of x? X to the third and x to the fifth. What do those two powers of x have in common? What is their greatest common factor? Great thing about finding the greatest common factors of powers of the same variable is that there's a simple decision process for doing so that always works. The greatest common factor of these two powers of x is x to the third, because both x to the third and x to the fifth have at least 3 powers of x in them. So x to the third is a factor of both. It's the greatest common factor because if we try to add any more x's into the mix, then x to the third isn't going to have enough, right, to take that many factors. So what's the simple decision process? Between x to the third and x to the fifth, which one do we know to take always? It's the smaller exponent. Whichever one has the smaller exponent is going to be the greatest common factor of these two powers. And so that's a pretty cut and dried. That's as cut and dried as any factoring method ever gets. So what that means is that we can also bring x to the third out into the front of our factor box from over here. And then the question is, if I bring x to the third out as one of the factors, then what am I going to put here as the cofactor attached to my 8? How many powers of x do we need to put here such that when I multiply it by x to the third, I get x to the third? How many x's do I want here? I don't need any, exactly, because all 3 of these x's are accounted for by this factor. So I'm not going to put any x's here. Or equivalently, we could put x to the power 0. Because after all, what is x to the power 0? What's it equal to? It's equal to 1. So whether we write it there or whether we don't write it there, we get the same expression, right? 8 times 1. So we don't need any x's then in my first term of my cofactor. How many powers of x do I need attached to this 7? Such that when I multiply them by x to the third, we end up with 5 powers of x. So how many powers of x are missing from x to the fifth if 3 of them are out here? We need 2 of them up there on top. Yeah, exactly, x to the 2. After all, when I multiply x to the 2 times x to the 3, what happens to those exponents? They add. Multiplying powers, we add the exponents, and sure enough, 2 plus 3 is going to give me the 5 that we're looking for. So, now that all this information is here, how do we finish the problem? What would we say is the complete factorization of 24x to the third minus 21x to the fifth? Well, we start by writing this greatest common factor out in the front, 3x to the third. Then, in a set of parentheses, we put the terms from our cofactor, 8 minus 7x squared. And we know that we have factored this completely because if I look at 8 minus 7x squared, those two terms have nothing interesting in common. The 8 and the 7 have nothing interesting in common, just a 1. And one of the terms has powers of x, the other one doesn't, so they don't share any powers of x in common either. So that must mean that I'm done. This is the first step up our factoring mountain, and it's kind of a big step, right? That first staircase up the mountain is a pretty high staircase to get us from the ground. But it does give us a pretty powerful tool. And it also serves for us as the first step in any factoring thought process. This should always be the first thing you try when meeting a new expression to try to factor. Because there will be a number of expressions that come to us that don't already have the greatest common factor taken out. But if you do take the greatest common factor out, sometimes the expression that you get that's right here is something we can factor additionally. It's not in this case, but in other cases it might be. And so from there, we would then use different factoring methods to continue breaking it down. So you can always, in any factoring problem, you can always check your answer. It's the most checkable of all problems in algebra. To check it, just remultiply this expression back out. And if I were to remultiply this expression back out, I would have to distribute this multiplication across this subtraction inside here. And so the 3x to the third times the 8 would account for my first term, 24x cubed. So I need the 8 in order to account for this first term. And 3x to the third times negative 7x squared would account for the negative 21x to the fifth for my second term. Factoring is kind of an art form in a way, right? We're going to talk about strategies for it today, but it kind of feels like some nonlinear thinking. You have to do a lot of thinking backwards and that kind of stuff. Factoring is hard. Going the opposite direction, multiplying things back out using FOIL, using distributive property, that's not an art, that's a science. Right? So probably the most useful thing you can do on a factoring problem is to check your answer. Multiply it back out, and what we should get is we should get back to the original problem where we started. If we don't get back to this original problem, then chances are we did something wrong in our factoring process, and we should either look back through for mistakes, or maybe we just took the wrong approach from the word go. But checking your answers is probably more useful, easier to do, maybe more important in factoring problems than in other types of problems. So that's our intermediate level factoring skill. Factor a quadratic trinomial whose leading coefficient is 1. So let me unpack the statement of that, because it tells you exactly what it is, but it uses this terminology that we should be sure to understand here. So the kinds of expressions that we factor here at the intermediate level are, first of all, trinomials. So how many terms do they have? Etymology of the word trinomial indicates that these are expressions with 3 terms in them. And the fact that it's quadratic means that the degree of these expressions is going to be 2, degree meaning the highest exponent. So we're not going to see x to the thirds, we're not going to see x's to the 10th. The highest exponent that we can see is going to be x squared. And so the other powers of x are just going to be x to the first power, and then x to the 0 power, which again, because that's equal to 1, that just indicates that we're going to possibly have some constant terms in it. I can put other coefficients inside here, so maybe I'll put an 8 here, and then how about a 7 or something like that. And then the leading coefficient means the coefficient that's attached to the highest power of x. So that's the coefficient that's in front of the x squared here. So in principle, and we will see this later on today, in principle we could have a number in front of the x squared that's not just 1. But in our first climb up the mountain, we have to learn how to do it when there's just a leading coefficient of 1, which is usually not even written expressly, right? We just leave it out. So this is the kind of expression that we learn to factor at the intermediate level. X squared minus 8x plus 7. So what does this kind of expression make you think about when it comes to approaches to factoring? What is going to be our thought process or your decision-making matrix for this? Remember that when I do this, I like to start with this little factoring grid again and put my x squared and my 7, my quadratic term and my constant term. I'm going to throw those in these 2 squares. And the reason I do that is because we're always going to factor x squared the same way. How are we going to break apart an x squared? X and x. If we're not breaking an x squared into an x and an x, then we're probably not making the most of our opportunity to factor. So we'll make our x squared into an x and an x. 7 happens to be a pretty nice number to factor. What are some ways to factor the number 7 into a pair of factors? Yeah, 7 really doesn't have a very interesting factorization. The only way to get 7 is to multiply 7 and 1. Yeah, exactly. So one option is to make it positive 7 and positive 1. And if we take that route, the nice thing about this little factoring grid that I have over here is that it just requires that we fill in those missing squares. I'll have a plus 7x from this square and a plus 1x from this square. And then if I were to combine these all back together, so this is my checking step again. If I combine them all back together, I'm going to get x squared plus 7x plus 1x plus 7. So how many total x to the power 1s am I going to get? I'm going to end up with 8 of them. So if this were my factorization, then when I multiplied it back out, I would get x squared plus 8x plus 7. So is this the correct factorization for our expression or no? It's not, because this middle term here doesn't line up with the middle term that we wanted. So how do we fix that? Yes, so let's make the 1 negative. If I make the 1 negative, but the 7 stays positive, then this square is no longer going to be positive 7. That would be negative 7. So that we don't want. So what else do we have to change? The 7. Yeah. We have to make both the 7 and the 1 negative. After all, the only way to get a positive product is to multiply 2 numbers that have the same sign. A negative times a negative, or a positive times a positive. But if we choose the negative times negative route, now when I combine my powers of x to the 1, negative 7 and negative 1 combine to negative 8. And that is exactly the expression that we started with. That's the other nice thing about this factoring method is especially if you use the little grid, the way that I'm using it here, the checking step is kind of built in. Right? We can just right now already check to see that when I multiply this back out, we get back to our original expression. And now that we've written that all out, how do we write our final answer? So we're going to factor this trinomial as a product of two binomials. And those two binomials are exactly the binomials that are in the purple and the green columns of my factoring grid. Scoot that over. So one of my factors is x minus 7. The other of my factors is x minus 1. And that's it. And again, looking back at what made this example work, and this is very often the way that people approach these, the way that it sticks in their brain, is that we were looking for two numbers which multiply together to equal positive 7, and those same numbers have to also add together to give me negative 8. So if we find a pair of numbers that satisfy both of these criteria, we have found the two pair of numbers that are the opposite terms in the binomial factors for x and x. Right? So here, negative 7 and negative 1 are the pair which multiply to 7 and add to negative 8. That's why negative 7 and negative 1 work in this factorization the way they do. At the advanced level, what we want to be able to do is use factoring to solve an equation. And the reason this is so important is that it convinces us why factoring is even useful in the first place. Why do we spend so much time in an algebra class worrying about how to factor expressions? This is why. It gives us the tools to solve an equation that we otherwise would not be equipped to solve by the regular decision-making processes of reversing the order of operations and simplifying and all that stuff that we learn how to do for simpler kinds of equations. So that's why we care about factoring. It's one of the biggest reasons to care about factoring, is it gives us this new approach. So let's take an example, and I want to make this example as rich and fully featured as possible. So the prompt here is going to be solve for x. So I'm going to give you an equation. Let's say my equation is 2x squared minus 10x minus 12 is equal to, oops, let me scoot this over a little bit so I have some room, is equal to x squared, how about squared plus 9. So here's an equation. I want to solve it for x. And what that means, first of all, the first thing you should remember about the prompt solve for x is it means that our answer needs to be x equals something. If we haven't gotten down to an answer that says x equals something, particularly a number in this case, if we haven't gotten there, then we're not done with the problem yet. Sometimes what people will do is they'll get halfway through this problem, they'll do the factoring step that we'll talk about, and then they'll stop. But we're not done until we finish with the process of actually solving, finding the values of x that balance both sides of this equation. So what should we do with this equation? It's got x's all over the place, it's got a quadratic trinomial on the left, it has a thing on the right that looks quadratic also. How are we going to make some progress toward getting the x by itself? What's the first thing you want to do? So just as with any equation, the first priority, if we have x's on both sides of the equation, as we do here, right, our first priority should try to be getting all the x's to one side. So, as Joe was saying, look and see if there are like terms on both sides of the equation that could be combined onto one side. And sure enough, there's an x squared term on the left and an x squared term on the right. And that argues that we can use subtraction to combine those like terms together. I'm actually going to do it by subtracting the x squared from the right, so that all the x's are going to move to the left side of the equation in this case. You'll see why I make that choice in just a minute, I think. And so on the left, I'm going to have 2x squared minus x squared. So how many x squareds am I going to end up with here? Just 1. That, by the way, is why I wanted to subtract it in the way I did, so that we get a leading coefficient of 1 here instead of negative 1. Yeah, it'd be negative 1 on the other side. Okay. And the other thing, and this is a little different with these kinds of equations, it's also going to be important to me to also move this 9 from the left side to from the right side to the left side. I want there to be an empty side of my equation after I'm done with all this movement. That is important to do in solving polynomial equations, and it's not as important to do if we're solving other types of equations. We can always do it, it's just more important now. So negative 12 minus 9 is going to end up with negative 21. So now I'm going to have on my left side x squared minus 10x minus 21. And then on my right-hand side, I'm going to have the most important number in all of polynomial algebra, 0. And that's an important number to have there. If I don't have a 0 on one side of the equation, I shouldn't even think about trying to factor anything. If I try to factor something before I have a 0 on the other side of the equation, it's not going to do me any good. If I tried to factor this thing, for example, or if I tried to factor that thing, it's not going to get me closer to where I need to go because it's not going to let me do the next step. Let's, now that we've gotten this expression on the left-hand side, let's factor it using what we talked about at the intermediate level. How can we factor x squared minus 10x minus 21? Two numbers which multiply together to give me negative 21, and which add together to give me negative 10. Yeah, so it looks like a 3 and a 7 are going to do it. And if I need, I'm going to make a quick modification to the problem itself. I'm going to change the plus in front of the 9 on the right side to a minus, and the minus on the 12 on this side into a plus. So my apologies, just changing the game. You don't get to do that on the exam, by the way. The exam problems have all been carefully checked to make sure that they work. This one that I just pulled out of thin air today was not guaranteed to work. But now it does, because I'm looking for a pair of numbers which when I multiply them together give me 21, and when I add them together I get negative 10. And what pair of numbers make that work? Yeah, a 7 and a 3 that are both negative. I need them both to have the same sign because they need to multiply together to a positive number. But I need them both to be negative so that they add together to give me a negative number. Okay. And so now we've done the factorization step that we learned at the intermediate level. And again, the caution I'm going to give people is it's tempting to stop right here, but we're not done. Right? We're not done until we've found out what are the values of x that actually make this equation true. So we need to have an answer that looks like x equals something. So now my question is, what can we do with this equation now that we've factored it and the other side is 0? This is the most key step in this whole process and the easiest to forget because you take a victory lap after you're done with factoring. Pull that victory lap back a second. What's our next step? Split the two factors apart. Take each of the two factors and give it its own equal to 0. Take one complicated equation and turn it into two much less complicated equations. The splitting step, for whatever reason, is the one that I think it's just people don't get enough practice with it because we spend so much time in our factoring units doing the factoring part and we don't dwell as often on the process of using factoring to solve an equation. And so it's this step right there. So don't get caught in the jungle and forget to, I don't know, I'm reaching here. Something to make you remember that step. Don't forget to split those apart. Because the great thing is, these two equations are dead easy to solve compared to any other equation we solved this semester. How do I solve x minus 7 equals 0? Add 7 to both sides. How do I solve x minus 3 equals 0? Add 3 to both sides. And now we have arrived at where we were supposed to arrive when we see a problem that says solve for x. Right? Problem says solve for x. We need to say x equals this. And at this point now, we have really two different responses to that question. What does x equal? X equals 7 and x equals 3. And there are our two solutions. So really the most important, well, two most important parts in this whole process. The first most important part is getting that 0 on one side. We shouldn't even think about factoring. It shouldn't even enter your mind until you have a 0 by itself on one side of the equation. So we use subtraction and addition, I guess, also in this case, to move all the terms from one side to the other and then combine the like terms to simplify them. If after that process we now have a quadratic trinomial, as we have here, that means that we can use the method for factoring quadratic trinomials that we already know to factor that, which is what we did here. And then comes the second most important step in this whole process. The whole reason that we factor is so that we can split each one of those factors into its own equation, equals 0. Those are much easier to solve, and so then we just solve them, and we're done. X equals 7, and x equals 3.